OK, so this is the setup of the question. We've drawn our stack diagram. We have reminded ourselves what parts of memory we can and cannot overwrite. And crucially, there's only one byte we can overwrite, which is this lowest byte of the SFP. So tiny little note, if you remember back to endianness, and you can go back and watch that video if that doesn't sound familiar, the lowest byte of the SFP, the one living at the lowest memory address, is the least significant byte. So for example, this SFP holds the address BFFFCD60, and it is the 60, the lowest byte, the least significant byte that I can actually change. And the reason why this is the least significant byte is because of the endianness and the fact that x86 is little endian. So just a little side note. But basically what this tells me is I can change this SFP to point somewhere else. So maybe the first thing I should ask myself is, where is it currently pointing? And what does the program do with this value that's stored on the stack? And why is changing it going to help me execute shellcode? So I think back to my stack frame and the way that I call functions. And I think, what does this value actually represent? Remember, this value represents the top of the previous stack frame. Because when the vulnerable function returns, this is the value that goes back in EBP. And when I go back to main, EBP should go back to the top of the main stack frame. So in other words, this value should tell me the top of the previous stack frame. And in particular, we haven't been super precise about what it means to be top and bottom of a stack frame. But if you go through all the steps of a function call, you'll notice that the SFP has a kind of nice property that it's the top of the previous stack frame. And in particular, we define the top of the previous stack frame, or any stack frame, to be its SFP. That's just how we design the stack frame. So for example, right now when we're calling the vulnerable function, EBP points at the top of the stack frame, which just so happens to be the saved EBP or SFP value. And this address, well, that happens to be the address of the previous SFP, because that's the top of the previous stack frame. And if someone else called main, then this SFP would point up here to the previous stack frame's top. So you can almost think of it as every SFP value holds the address of the previous stack frame's SFP. And that's another way of saying this value holds an address, and that address is the address of the top of the previous stack frame. So to make a long story short, each SFP holds the address of the previous SFP, which is kind of convenient. So how is this useful? Like, who uses this address? Why did I put it here? Well, the reason why I put this here is because when this function returns, this is the value that's going to go back in EBP. And that's kind of useful. Maybe another way of putting it is, when I put this value back in EBP and I restore the original main stack frame, well, I can now start thinking, what does the program do with this address? Well, the program uses the base pointer. I guess this is something I haven't really said explicitly, but I'll say it now. The program can use the base pointer to find other values on the stack. So when I put this value back in EBP, it's useful because it allows me to orient myself on the stack and find other things. So for example, if the EBP is here and I ask, hey, where's the first argument? I can start from the EBP, look 4 bytes up. OK, that's the RIP, and look 4 bytes up. If there was an argument, it would be right there. Or I can ask, hey, where's the 7th argument? Well, I started the EBP and count my way up to the 7th argument. So the base pointer is kind of useful for orienting yourself on the stack. Something I probably should have mentioned a couple videos ago, but I didn't, so here we are. So to make another long story short, the SFP, because it holds the value that's going to go in EBP, it's a convenient way to orient yourself on the stack and to help the program find other values on the stack. And one value that I really care about finding is the RIP, because that's the value where if I overwrite it, I can probably make bad things happen. So as an example, let's pretend that we could ask this program some questions. Like if we walked up to this program and we said, hey, program, where is the RIP of vulnerable? Well, how would the program find it? It would look at where its EBP is currently pointing. That's right here. And it would look 4 above that because it knows the EBP is always pointing at the SFP. And if I look 4 above that, that's where the RIP is. Now, what if I walked up to this program and I said, hey, where's the RIP of your previous stack frame? So for example, if it's currently invulnerable, hey, what's the RIP of main? How would this program know how to find the RIP of main, given all of the data in memory and all of the values in the registers? So you can pause and think about that. If I went up to this program, and programs can't talk, but if I asked this program, hey, where's the RIP of main, how would it know where to find it? And remember, we can use the base pointer or the saved value of the base pointer as an anchor to help us find things. So I think the way that the program would find the RIP of main is it would look at this address and say, well, this address is the SFP of main, the SFP of the previous function, so I should just follow this address and look for above that. That's how I know that this is the RIP of main. So the program doesn't label things in this pretty diagram, but the program would say, I'm going to look at this value, go to that address, add 4. That's where the RIP of main is. So all of this is to say the EBP and the SFP, which is just the saved version of EBP from the previous stack frame, is useful for finding things on the stack. And in particular, the way we can find the RIP of main is we can take this value, go to that address, that's the SFP of main, add 4, find the RIP. So that's what this value does, helps us find the RIP of main. So if this is the value we use to find the RIP of main, and I control what this value is because I can change one of the bytes, what if I changed this value? What if I changed this byte? Well, then the program would start looking somewhere else for the RIP of main. So let's see what that looks like. So let's say I take this value, which used to say 60, and I change it to 44. You could have changed it to something else. I picked 44 for reasons we will see. So now, this address, it used to hold the address of SFP of main, now it holds the address of something down here in main. But the program doesn't know that we changed it. The program is not expecting someone to come along and change the SFP. That's not supposed to happen. So if I now walk up to this program and ask the program the exact same question, hey, where's the RIP of main? What's the program going to do? It's going to do the exact same thing. It's going to say, if I want the RIP of main, I'm going to take this address, I'm going to go to that address, this must be the SFP of main, and if I look for above that, I must get the RIP of main. So the program follows the exact same logic, even though we messed up the address, because the program has no idea that we just overwrote something that we weren't supposed to. So in other words, if we now ask the program, hey, where's the RIP of main? It's still going to follow this address, go to what it thinks is the SFP, look for above that, this must be RIP of main. But in fact, it's not the RIP of main. The program thinks that it is, but we, the attacker, know that we are actually somewhere in the name character array, which crucially is some part of memory that we control. So this is the idea behind the off by 1 attack. The idea is we can't really target the RIP of the vulnerable function, but we can target this value, and this value, the SFP of vulnerable, is how we find the RIP of main, the previous function. So remember, to summarize it once again, in normal function execution, if nothing went wrong, and I went up to this program and I said, hey, where's the RIP of main? What it would do is it would take this value, SFP of vulnerable, it's an address, go to that address, look for above it, that's the RIP of main. That's what it would do. Take this address, go to that address, look for above. That's just how you find things on the stack. But if I take that address and I switch it up without the program really knowing that I switched it up, the program would still do the same thing. If I ask, hey, where's the RIP of main? It would take this address, go to that address. It thinks this is the SFP. It's not, but the program thinks it is. It would look for above that and say, that must be the RIP of main, but it's actually not. So basically, we've tricked the program into thinking the RIP lives down here, even though it really lives up here. And now that the RIP is thought to live down here, we've tricked the program into looking here for the RIP, we can now put the address of shellcode here, because the program is going to look here for an RIP. So now we put the address of shellcode here, and we write shellcode into memory somewhere, and we're all set. So the off by 1 attack crucially depends on the fact that I can change just this 1 byte, and by changing this 1 byte, I cause SFP to point somewhere else. So this address, instead of being the address of the real SFP of main, it's the address of some other thing that I control, which I will now call the fake SFP. And if you look for above that, the program thinks this must be the fake RIP, but it's actually not. It's something that we control. So now we just have to fill in everything else. This is the key idea behind the exploit, but now we just fill in everything else. So for example, we can fill in the address of shellcode here. So pretend that there's some malicious code at deadbeef, then I will just write the address deadbeef here. If I was writing shellcode into memory myself, I might have to write shellcode myself and then make this the address of shellcode. That would also work fine. But basically, once I have this exploit all set up, I just need to know where is the fake RIP and write the address of shellcode there, as my normal buffer overflow exploits do, and I'm all done. So that's the key idea behind this exploit. And in the next video, I'll show you what it looks like when the functions actually return.